Okay, good morning. Today we have the first exercise sheet which is going to be distributed, and if you don't get a copy, we have some more copies in front, so you can get some more copies when you leave the room afterwards, after the lecture. This exercise sheet, as I announced, maybe I write it down again so that no one forgets. This exercise sheet is due next Friday, and on Tuesday and Wednesday there will be no lecture. So there will be no lecture next Tuesday and Wednesday. So no lecture and no exercise course next Tuesday and Wednesday. And the first exercise course, which is the point where you have to return this exercise sheet, will be next Friday. So the first exercise will be next Friday, so today in 1 week. And another announcement, this exercise sheet, the exercises are given in English, but whether you work on them in German or in English is up to you. So you can work on it in German or in English, whatever you prefer. Okay, so what did we do? We started with introducing the syntax of the functional programming language Haskell. And maybe this is, I don't know if this is better, maybe not. And we introduced the following grammar. So a Haskell program is a sequence of declarations, and declarations are currently either type declarations or function declarations. Type declarations simply introduce a set of variables, variable 1 until variable n, which have a certain type. And a variable in Haskell is simply a string starting with a lowercase symbol. What is a function declaration? A function declaration is the left-hand side of a function and the right-hand side of a function declaration. Left-hand side simply says, this is the name of the function, and these are the arguments of the function. And the right-hand side says, equality sign, and then the expression, which should be the result. So, for example, is square of x equals x times x. Moreover, you can also use conditional equations, and there can be many conditions. And conditional equations have the form vertical bar and then a Boolean expression, equality sign expression. And this means the result of the function is, to compute it, we first evaluate this Boolean expression. If it's true, then the result is this. If it's not true, then we look at the next condition. We had an example for this with this maximum function. And then, in particular, we looked at pattern matching in the last lecture, and we saw that instead of using these conditions, it's often much more elegant to use pattern matching. And here are some examples for pattern matching. Let's start with the ones on the left-hand side, maybe. So pattern matching we had, for example, for Booleans, and we had it also for lists. So if you want to define a length algorithm, so this length algorithm, well, first you have a type declaration, so you introduce this variable len, and it has the type, which is on the right-hand side of this double colon. So it takes as input a list, and this data, or a or something like this is written with a small letter, so it's a variable, and this is a variable which stands for types. In other words, you can apply this length function to lists where the elements of the list may have any type, and the result will be an integer. And now pattern matching means you describe the form of the argument using a certain term, and basically this term simply contains variables and data constructors. So the data constructors for lists are the empty list and colon. And then you say, okay, the length of the empty list is something, 0, and the length of a list which is not empty, which is built with this colon constructor, is computed in a different way. And you can also write something like this. Here again, we describe the form of potential lists using the constructors empty list and colon, but there we have 3 cases because we want to compute the second element of a list. And pattern matching you can do for any data structure, including integers. For integers it's a bit strange because their pattern matching works in a bit non-standard way. So whenever you write something like x plus 1 or x plus 2, this will only match natural numbers. So this up here means you do pattern matching, so this is a factorial function, and if the input is 0, the result is 1. And this pattern matches only natural numbers which are of the form something plus 1. So, for example, if you call factorial of 2, then x would be 1, because 2 is 1 plus 1. So factorial of 2 would be 2 times factorial of 1, and you get this recursive call. And similarly, you can use patterns which look like x plus 2 or x plus 3, and so on. But the only pattern, but for negative numbers, this will be undefined. So if you call factorial of minus 5, you would get a program error. If you want to avoid this, then you have to add some more equations which cover negative numbers as well. Okay, so this is what we did in the last lectures. And you get already a feeling for what patterns are, because patterns are these special terms which describe potential inputs. And you can also, in addition to function declarations and type declarations, you can also add pattern declarations, which simply look like function declarations, but now you simply say, well, I have a certain variable or a certain pattern, and I say this pattern should have a certain value. Let me give you an example. So this is the next component in these very basic components of Haskell. We also have pattern declarations. And pattern declarations are almost like function declarations. But for a function declaration, the left-hand side always looks like this. The left-hand side has first the name of the function and then a sequence of arguments, a sequence of patterns describing the potential arguments. So you have at least 2 items on the left-hand side of the equation. And for pattern declarations, you have just 1 item on the left-hand side of the declaration. That's it. The only difference is this. The function declarations, they would look like variable and then pattern 1 until pattern n equals expression, or they would be conditional, and n would be greater or equal than 1. And for pattern declarations, they would look like this. You have just a pattern and then an expression. So here you have at least 2 items, namely the name of the function, and then at least 1 argument, probably more. Here you have just 1 item. Let's look at some examples to illustrate this. So here are examples for pattern declarations. Now this is a very simple one. So a pattern, examples for patterns are, for example, variables, and variables we denote by strings starting with small letters. So, for example, the string pin would be a variable, or x, or whatever. So we can now write something like this, and, well, what happens here is you simply declare a constant. This should be the constant pi. Pi is predefined in Haskell, therefore I called it pin. I didn't come up with a better name. So if you want to declare a certain constant for pi or for pin, you can just write this. This should be the constant which has the value, well, something like the number pi. You can also see that in addition to integers, there are also other numbers in Haskell. There's a predefined data type float for floating point numbers, which works pretty much the same way as the data type for floating point numbers in any other language. Notation is also the same as in other languages, so there's no big surprise here. So the only difference is this is not a function which takes arguments, because you don't give any argument to pin. It's just a constant. But there are other forms of patterns. For example, this. Now this would also be a pattern. So again, this is a variable. I mean, it's a string starting with a lowercase letter. Now what do we say here? This is also a constant suc. It has the type int arrow int. So it's a constant of function type. It's a constant which, and the type of this is, it's a function from integers to integers, and we can define it like this. Now this looks strange at first sight, but you remember in the last lecture we introduced the concept of currying. So currying means instead of having functions with higher arity, we just use functions with arity 1. And you can give arguments one after another to these functions. So if you remember, we defined a function plus like this. We said this is a function which first takes an integer, and the result will be a function from int to int. So if we write it like this, then it is the same as if we would write brackets like here. So plus is a function which takes an integer, and the outcome is another function which waits for an integer and then would add these two integers. So in other words, plus 1 is the function from int to int, which increases its argument by 1, or which adds 1 to its argument. And we can give a name to this function and call it suc for successor. So in other words, what we define here is the function successor, and the successor function is simply the function which adds 1 to its result. Now, of course, you could also define this function in a different way. You can also write this, but that would be equivalent. So you can write this. This would be a natural definition for the successor function, but you can also write what is on the slide above. It would do the same thing. And if you give an argument to suc, for example, 2, so if you would give the argument 2 to this function, then what would happen is you would first compute plus of 1, and then you would apply this function to 2, and the result would be 3. So indeed, the suc of 2 would be 3. So this is something you can do as well. Now we had variables as patterns, but there are other forms of patterns. For example, tuples are also patterns. So if pet1 and pet2 are patterns, then the tuple of pet1 and pet2 is a pattern as well. So something like pattern 1, pattern 2, or n patterns. So the tuple of n patterns is also a pattern. And therefore you can write a declaration like this. So here we say, well, this pattern, the tuple of x0 and y0, should have this value. It should have the value tuple of 1 and 2. And the effect of this is, after this declaration, if you want to know what the value of x0 is, well, the value of x0 will be 1, and the value of y0 will be 2. So, intuitively speaking, a pattern is a term where when you assign a value to this term, then it's clear which value all the variables in this term will have. So, a general idea. So patterns are special terms such that with the following property, if you assign a value to this pattern, then it's clear which value each of the variables in this pattern will have. Such that if one assigns a value to the pattern, like we do it here. Here we assign the value tuple of 1, 2 to this pattern. If one assigns a value to a pattern, then it is clear which value each variable in this pattern has. And indeed, this is the case here, because if we assign this value to the pattern tuple of x0 and y0, then it is clear which value x0 will have, namely 1. Now, there are other forms of patterns. For example, we've already seen that patterns are patterns can be terms built with data constructors. So, terms built using data constructors. So for example, it could be a pattern like take pattern 1, and then you use the data constructor colon, and then probably you take pattern 2, and again data constructor colon, and then the empty list. And this is the same as writing this shorthand notation, pattern 1, pattern 2. Now again, this colon operator associates to the right, so if you write this, then this is the same as writing that. So this is a term which contains patterns and combines these patterns with using constructors. Constructors are function symbols where you have no algorithms to evaluate them further, but these function symbols are only introduced to introduce data structures, to build objects of a data structure. And again, if you assign a value to this list pattern, then it will be clear which value will be assigned to all the variables in here. For example, look at this. Here we say this pattern, so the list with the elements x1 and y1 should have this value. Now if you do this, then it's immediately clear what will be the value of x1 and what will be the value of y1, namely 1 and 2. Now this would be a pattern as well, and that is again something you can write in Haskell. And what happens here? Now this you can do as well. Again, obviously this is a pattern. I mean, these are variables, x2 and y2, so they are patterns. And we combine these two patterns with a data constructor colon, and we say x2 colon y2 should be this list. Now if we do this, again, it should be clear what value x2 will have after this assignment and what value y2 will have after this assignment. So what do you think are the values of x2 and y2? Mm-hmm.
x2 is 1 and y2 is the list with element 2.
Right, exactly. Now that's the difference. Here y1 is number 2. Here y2 is the list containing 2. As you can see here, x2 is an integer, but y2 is a list of integers. This means insert x2 into the list y2. Okay, so this is something you can do as well in Haskell. And in order to deal with this, we have to extend our grammar again. So let's do this. And if we extend our grammar, it will look like this. So this is the grammar as we had it up to now. And now we have another form of declarations, namely we have also pattern declarations. So now declarations can be either type declarations or function declarations or pattern declarations. And pattern declarations, how do they look like? Well, it's a pattern, and then it's a right-hand side. So that's the only difference to function declarations. Instead of writing name of the function and then forms of the arguments, now you simply write a pattern, and then afterwards you have the right-hand side, just as before. So you can also have conditions on these right-hand sides. You can do the same things that you did for functions as well. Okay, so these are pattern declarations. Now, another thing that we have to introduce is, so we are almost done. There's not too much coming on for declarations anymore. But one thing you can do in Haskell, and which is similar to things you can do in other languages, is you can have local declarations. So in many languages, you have something like parts of the program which are not global, but which are embedded into some other parts of the program. And something like this exists in Haskell as well. And in particular, this has advantages concerning efficiency. And I will try to illustrate this. So these are local declarations. And these are declarations which are not on the top level. I mean, up to now, a program is just a sequence of declarations. They are all on top level. So these declarations define functions or constants, and you can use these functions everywhere in your program. There's nothing like any structure. I mean, it's just listed one after each other. And that's not always what you want to do. And so you can also now have local declarations, which means you have declarations which, again, inside contain more declarations, which are local. And How can you introduce local declarations? Local declarations you can introduce by adding the keyword where. So inside a declaration, inside a function declaration or a pattern declaration, one can define local declarations using a keyword, namely using the keyword where. So let's look at an example. Now maybe before we look at an example, let's add this to the grammar. So I modify this grammar again, and I will show you where it is modified. So this is the same except for two changes. And these are the changes. So in a function declaration, up to now we had this left-hand side saying name of the function and then the arguments. And then we had the right-hand side, which consists of equality sign and result. And now if you want to, you can add this part. So these square brackets in the grammar notation mean you can add it, but you don't have to add it. So if you don't like to, you don't add it. If you like to, you do add it. So this is the meaning of square brackets. So square brackets in the grammar mean, so this means this can be added, but doesn't have to be added. So but doesn't have to. So everything that was legal Haskell code before is still legal Haskell code. And now, so if you want to add this, then simply after your function declaration, you write the word where, and then you write many more declarations. So decals stands for many more declarations. What does decals do? Decals simply starts with a curly bracket and then a number of declarations. These can again be new function declarations or new pattern declarations separated by semicolons. And then at the end you do a closing curly bracket. And that's it. And you can do the same thing for patterns. Again, you can write, if you want to, where, and then a sequence of new declarations. And these declarations are local, which means that these declarations are only valid for this particular function or pattern declarations. And outside these declarations, they are not visible. So let's look at an example. So here's an example. And now this example computes something sensible. What we want to do is we want to solve equations with binary polynomials. So in other words, we want to solve an equation like this. A times x squared plus bx plus c equals 0. So a, b, and c are numbers, floating point numbers, and we want to look at the roots of this binary, of this polynomial of degree 2. In other words, we look for all x's which solve this equation. Now, how to do this, you hopefully learned at high school, because this is typically what high school students have to learn. So there's a formula which you can learn by heart if you forgot how to solve this. If you forgot how to solve this, you don't know it by heart. So either you know the formula by heart, or you can easily find out how this formula looks like. I will tell you. So I hope this looks very familiar to you. To compute this, there are at most two solutions. It's minus b plus minus square root of b squared minus 4ac divided by 2a. So I hope this looks very familiar to all of you. If you don't believe it, then you can easily verify that this is true. Now, obviously, this doesn't always have a solution, because this stuff can be negative, and it can also happen that this stuff is 0, then it has one solution, and there are also cases where it has two solutions. So a, b, and c are numbers, and we look for all x's which solve this. Now, if we want to write a program which does this computation, it might look like this. So these are the roots, Nullstellen, of this polynomial. So roots takes three floating point numbers, a, b, and c. So float, float, float. And it will return, well, it will return 2 floating point numbers because this in general has 2 solutions. So the outcome will be a tuple of 2 floating points. And how do we compute this? Well, we simply encode this formula into Haskell. So this is the function declaration, roots of A, B, and C. And, okay, plus, minus, times, square root, this is all predefined. So, I mean, writing this in Haskell notation is a very easy task. And we could do this, of course, but this will look, well, it will look ugly and it will take a lot of computation time. So it's a better idea to compute the following thing. Because you can see we have the problem that we compute 2 results. So one time we compute this result where we write plus, and one time we compute this result where we write minus. And if we compute these 2 results independently, then this stuff and this stuff has to be computed twice. I mean, we would first compute the result where we write plus, and then we compute this complicated square root and do this multiplication. And then again we compute it where we write minus, and again we compute exactly the same stuff. Now that's not very clever. We should only compute it once. So let's give this a name. Let's call this D and let's call this E. And then we know how to do this in a more clever way because we know how the 2 results look like. The results are minus B minus D divided by E and minus B plus D divided by E. And now, of course, we have to say what D and E are. And here we use this where. So, where D is square root of B times B minus 4AC, minus 4AC, and E is 2 times A. So this illustrates how this idea with local declarations works. So this is a function declaration. We say this function applied to these arguments, A, B, C, is this result. And there are some more declarations because here we declare what D is and what E is. But these declarations are local. So these declarations only concern this right-hand side and nothing else. So if we write D here, then we know what D is because D is declared here. But outside this declaration, D is unknown. So if we are outside of this function declaration and we now write the next function declaration, D is unknown, E is unknown. D and E are only, this definition of D and E is only visible inside this declaration and not visible outside. Okay, this is not a very surprising concept because you have similar concepts in other languages as well. What is important is by writing, I mean, of course you can write this program without local declarations. You can, instead of D, you always write this big term, and I forgot a closing bracket. And instead of E, you write this term. This will get less readable, but moreover, it will also get less efficient because the realization of Haskell is the following. Haskell will notice that here you have D, here you have D, and there's just one D which computes this result. And so the realization will be, this will be realized as a pointer to some cell in the memory where you have square root B times B minus 4AC. So whenever you start evaluating this, because you want to compute the result, you don't evaluate it twice, you only evaluate it once. So this is going to be realized as a pointer. So this will be some pointer which points to this. And this E will be some pointer which points to this. So the important remark is by using a local declaration, the value of D and E is only computed once. And if we wouldn't do this, if we would replace these occurrences, these two occurrences of D by this term, and these two occurrences of E by the term 2 times A, then in order to compute the whole result, all these terms have to be evaluated twice.
Question aside, would I be able to carry the results? So I don't have a pattern, parentheses, float parentheses, but float, pointer float.
I didn't quite understand this. What?
I want to know if the right hand is a pattern with two values.
You mean this?
Yeah. Could I carry this also?
Okay, so what you want to do is you want to replace this tuple here by float, arrow, float.
Yeah.
Well, there's a difference between these two types. So this here is a tuple of values. So here you might have something like, I don't know, -2 and 2. You could imagine that this is the solution for some of these equations. This is a function from floats to floats. Now, how do you want to encode an object like this as a function? I mean, you can think of some strange encoding. For example, a function which for -2 and for 2 it returns 0, and for everything else it returns 1. So if you think of a very strange encoding, yeah, you can do this, but it's a not very natural encoding and not a very good idea. So if these are the objects you really want to represent, then this is the much more natural data type. Encoding it as function is overkill. So you can do it, but it's not recommended.
Okay.
So there's really a difference. If you have tuples as arguments, then going from tuples as arguments to a curried form like this represents the same information. So you don't lose anything, you don't win anything as far as the information is concerned. You win something because you save some parentheses and you can do this partial application. But apart from this is the same. If you have tuples as results or functions as results, that's a big difference. So this is not really the same. This carries much more information than that. I mean, these are essentially an infinite number of pairs, because you have, for every floating point number, it's an infinite set, because for every floating point number, you have another floating point number, which would be the result of this function. And here you have just one pair. So this carries much, much more information, and is really something completely different from that. So this is the better idea here. So by using local declarations, the value of D and E is only computed once, and if one would replace the two occurrences of D here, the two occurrences of D by this square root term, so square root of this, then this term would be evaluated twice, which is less efficient. So this would be inefficient. So the reason for local declarations is twofold. One reason is readability gets better, and the other reason is efficiency is improved. And that's the reason for introducing something like this. And to improve readability even further, Haskell has a peculiar way of saving brackets, which I will introduce to you now. So what comes now is pure syntax. So if you like to write it like this, then you can write it like this, but typically people don't write it like this, but they drop the parentheses. And as I already mentioned in the beginning, Haskell is one of the few languages where it matters how many spaces you add. So in other words, if you write your program, layouts of program, you should lay out your program in a nice way in every programming language. But if you do it or if you don't do it, that simply influences the readability of your program, not the execution in other languages. In Haskell, that's not true. In Haskell, if you lay out your programs nicely, you are rewarded because then you can save brackets. And so easier readability or better notation. For better notation, you can use the so-called offside rule. for denoting declarations and local declarations. And the goal is you can save parentheses. So you can drop some of these parentheses. And this offside rule, in fact, there are 4 rules. So the 4 rules are, what you have here is basically a block of declarations. So these declarations are all on the same level. In this example, we had 2 declarations because we declared D and E. So D and E are declared at the same level. Obviously, these declarations can again have local declarations and so on. So you can have many declaration blocks nested into each other. And the goal is not to write these curly brackets and not to write these semicolons. And then what you can do is you simply write these declarations below each other and you don't write any brackets. And then the question is, when does a declaration block start and when does a declaration block end? And the rule is, the first declaration in your block, the position of the first symbol in this block determines in which column all the lines of this declaration have to start. So the first symbol in a declaration block, or in a sequence of declarations, determines the left border of the declaration block. I will give an example in a moment. So if you decide to drop these parentheses, you can do this, and then the first symbol of declaration 1, the position where you write it in your program determines where this block starts. And if you start a new line, which starts at the same position, so in the same column, then this is considered to be a new declaration within the same block. So a new line which starts at this same left border. So not one symbol to the left, not one symbol to the right, but exactly there, is a new declaration in the same block. In the same block. So, for example, to illustrate this, suppose this is the first line and this is one declaration. D equals square root of something. And then if in the next line you start exactly below this, then this is considered to be the next declaration in the same block. So this must be really below each other. And now what happens if the next line starts not below this, but maybe here to the right, or maybe there to the left? Now that means something. If it starts to the right, then this is considered to be a continuation of the line before. I mean, if you have a very long declaration, it probably doesn't fit into one line. Then you can continue in the next line, but you may not start below this. You have to start somewhere to the right. So a new line which starts on the right to the left border, so somewhere here. So this is not a new declaration, but this continues the declaration in the line before. Belongs to the same declaration as the line above. So for example, if your screen is very, very small and D equals square root B times B minus 4AC doesn't fit on your screen, or if you program on your PDA or on your mobile phone, you have Haskell for mobile phones maybe, then you probably have to start here. Okay, and now your screen is over, and then you want to continue with minus 4ac, then where do you have to write it? Not here. No, not here, because your declaration starts here, but if you continue it somewhere here, then that's fine. So this new line is not considered to be a new declaration, but it's considered to be something that continues the stuff in the line above. And now the last question is what happens. So this would happen if you suddenly write something which starts to the right of this left border. And now the question is what happens if you write something which starts to the left of this left border. And that means this declaration block is now over. So as soon as you write something which is not below this or to the right, but to the left, then this ends this declaration block, and this is a new declaration outside this declaration block. So a new line which starts to the left of the left border. Now this is strange English, but I guess you understand. Means that this is the end of the declaration block, that the current declaration block has ended, and this new line does not belong to this declaration block anymore. Doesn't belong to the declaration block. So with these rules, you can now write programs with declarations, in particular with local declarations, using the layout, using indents, Einrückungen, instead of using brackets. So maybe I just modify this roots program to show you how this would work. So the goal would be, we want to remove these brackets. Now this whole stuff is a declaration block. This declaration block, D and E are defined in this block. This declaration block is local to this declaration block up here, which defines roots. So what we would like to do is we would like to remove these brackets, and we would like to remove this semicolon, and we would like to remove this bracket as well. And in order to do this, we cannot leave it like this, because now we start with this declaration, but this is a new declaration. This is in the same block as this, but it's not the same declaration, so it may not be in the same line. But we can write it into the next line, and it must be exactly below this D. So here we would have to write something like this. And now these two declarations are below each other, and that means they are in the same block. And this block is to the right of this block, so this is a local block for this. And if we now in the next line start defining something else, maybe square is whatever, a function from integer to integer, then this new declaration is to the left of this, which means that now the declaration block is over, and this is a new declaration on top level. So this means to make local declarations more readable, don't write these parentheses and don't write semicolons, but write the declarations below each other. And if your line is not long enough, then continue to the right. And if your declaration block is over, then go to the left again. So this is what is typically done in Haskell. So nobody writes these curly brackets, but you would rather write it like this.
Is 10 equal to white spaces in
That depends on your editor, and is a disadvantage of this rule, because you can never be completely sure that when you save your file and you switch operating systems, that this still works in the way you expect it to be. So that's a disadvantage. Try it out. Try it out with your editor and see how it works. Okay. But in general, this is still a nice way to read. This is pure syntax. So this has, I mean, you can avoid this if you don't like it, but typically people use it. Okay, so the last thing that I want to say about declarations is, again, something that is more or less just syntax. And that is the declaration of operators and of infix declarations. So operators and infix declarations. So to ease readability, very often, or there are many cases where you don't want to write a function in prefix notation, but in infix notation. So some functions are usually written in infix notation instead of prefix notation. So this means that instead of writing first the function symbol and then the arguments, you write the function symbol between the arguments. Now, there are prominent examples, for example, plus, minus, equal, and so on. You typically write 2 plus 3 instead of something like plus of 2 and 3. So this would be prefix notation. First the function, then the arguments. This is infix notation. The function stands in between the arguments. And from everyday life, you are very used to do this. You typically write 2 plus 3, 2 minus 3, 2 equals 3, 2 greater 3, or smaller 3. So, I mean, this you just like to write in everyday life. So Haskell supports this as well. In particular, you can define such infix operators yourself. And so infix, such function symbols, such binary infix function symbols are called operators. And when you define functions yourself, up to now we only define prefix functions, but if you like to, you can also define infix functions. So they can also be defined by the user. By the user, well, by the programmer, by the Haskell programmer. By you, so to say. And how would you do this? Well, there again, this is pure syntax. If you don't like this, you don't have to use it, but it eases readability. And again, there's syntax. Now again, you have to distinguish between variables and constructors. For prefix symbols, variables are strings starting with lowercase symbols, and constructors are strings starting with capitals. So we remember, for prefix symbols, we had variables is a string starting with lowercase symbol, and constructors like true or false are strings starting with uppercase symbols. Now for infix symbols, these are sequences of special characters, Sonderzeichen. So not something like the letters A, B, C, D, E or so, but special symbols like plus, minus, equality sign, colon, comma, dot, whatever, dollar, maybe euro if you have a very modern version of Haskell. And to distinguish between this, to distinguish between variables and constructors, the convention is like this. Constructors are sequences of special symbols starting with colon, and variables are sequences of special symbols which don't start with colon. So variables are sequences of special symbols. So that means no letters, no numbers. Well, with numbers I'm not so sure, but no letters. But not starting with colon. So examples for such variables are, for example, plus. I mean, this is a one-element sequence with a special symbol, and it's not colon, or minus, or equal, equal. This is a two. I mean, this has two symbols. Both are not. The first one is not colon. The second one might be colon. So something like this. These would be variables. So they are defined functions which don't start with colon. And constructors have to be. Infix constructors are the same, but they do start with colon. And we have one example, namely colon itself. This is the one-element sequence just containing colon. This is the constructor for lists. It's an infix constructor because you typically write x colon x's, and that is the that represents the data object you get by inserting x into x's. But you can define such stuff yourself. Let's do this in a moment. Now, sometimes you want to switch between prefix and infix. And you can do this. So every prefix symbol you can also turn into an infix symbol, and every infix symbol you can also turn into a prefix symbol. Again, how do you do this? So every infix symbol can be turned into a prefix symbol. Prefix symbol by putting round parentheses around it. So for example, there is the prefix symbol plus, because you write 2 plus 3. If you want to make a prefix symbol out of it, you write this. This is a prefix symbol, so you can now write this instead of 2 plus 3. So whenever you have an infix symbol, no matter whether you defined it yourself or whether it's predefined, you can make a prefix symbol out of it by writing round parentheses around it. And you can also do it the other way around. So every prefix symbol can be turned into an infix symbol by using backquotes. Backquotes look like this. So if we define plus as a prefix symbol and you want to make an infix symbol out of it, you can write 2, and now in back quotes you write plus instead of plus 2, 3. So this is, again, just notation. Now, of course, it's still unclear how to introduce new infix symbols, and moreover, with infix symbols you have some problems. If you write something like 2 plus 3 times 4, then, and you write no brackets, then the question is, what is the result? Do you first execute plus, or do you first execute times? Now, for plus and times, Haskell does it the right way, but if you define such stuff yourself, then you have to decide what to execute first, and you can tell this to Haskell. Okay, let's look at an example. So there are two problems. One problem is, let's first look at the problem when you write something like 2 plus 3 plus 4. So we use the same operator, plus, but we use it twice. Then the question is, which one do you execute first? Now for plus, that doesn't make a difference because it's associative, but not every function is associative. And this is the problem of association. So there are two problems with operators, or with infix operators. And one problem is association. And to illustrate the problem, I will define a divide algorithm, which in division is not associative. So let's say divide does the following. It takes two floating point numbers and divides them by each other. So divide of xy should be x divided by y. This is the predefined division of Haskell. And now the question is, how should one evaluate an expression like this? I mean, we can make an infix symbol out of this divide by adding back quotes. So we could write something like 36 divide 6 divide 2. And now the question is, what will be the result of this? Now there are two possibilities. If you first execute this divide, you will divide 36 by 6. The result is 6 divided by 2 is 3. Or you first execute the second divide. Now 6 divided by 2 is 3. And then you divide 36 by 3, which will give 12. So for plus, it doesn't matter if you first execute the first plus or the second plus. But for divide, it does matter because divide is not associative. Well, and since you defined this program, you should decide what you want. So for some functions, it might be sensible to associate to the left, and for some, it is sensible to associate to the right. And you can decide this yourself. And therefore, you can add another declaration. So we will give another form of declarations, infix declarations, where you tell Haskell whether this associates to the left or associates to the right or doesn't associate at all. So one, and one means the programmer, one has to determine whether divide associates to the left or to the right. Or to the right or not at all. And depending on this, you can add the following declaration. So one would add the following infix declaration, which has the following form. You simply say infix L. L stands for left. And now you say that this, so if you add this declaration, like the other function declarations, pattern declarations, you can write this declaration as well. And that means this operator associates to the left. So if you add this, then you would execute this one first. Then it would mean this is interpreted in the way that you would add parentheses to the left whenever you have an expression like this. So then the result would be 3. If you instead write infix R, divide, then it would associate to the right, and the result would be 12. So this means associate to the left. This would mean associate to the right. And you can also say, I don't want to have expressions like this. Such expressions are illegal. Whenever the programmer writes something like this is a program error because the programmer should write brackets if he writes something like this. If you want this, you can say infix without L or R, divide, and that means no association, and then this would be an error. Then Haskell would not accept expressions like this. And if you don't write anything like this, then the default is association to the left. So this is the default. And, well, we had already some examples. So, for plus and for times, it doesn't matter whether you associate to the left or to the right because the result will be the same. But we had, for example, something like this function constructor, something like the function from A to B to C. This is considered to be the same as A to B to C. So this associates to the right. And we also had something like function application. If you write plus 2, 3, then this is considered to be the same as first apply plus to 2 and then apply to 3. So this associates to the left. And this indicates that both can be sensible. There are cases where you want association to the right. There are cases where you want to associate to the left. So maybe to make this clear again, if you write something like square of 3, if you write this expression, what would happen? So there are two possibilities. What will be the outcome?
With association left, there should be a program error, and with association right, it will first compute square 3 to 9, and then square 9 to 81.
Correct. Right, and association is to the left. Function application is to the left, so this will be a program error. But you're right, if association would be to the right, the result would be 81. So this would be considered to be this, and that's a type error. Square has to be applied to an integer and not to a function, so this is a program error. So this is not type correct, and therefore will be an error due to this reason. So you need to know about association. Now, association is not the same as associativity. Divide is not associative, clearly, because it matters whether you first execute this divide or this divide, so this division is not associative. And exactly for those operators that are not associative, it matters how you declare this association. Should things associate to the left or to the right? If the operator is associative, then it doesn't matter. Now, that's one thing you have to think about with infix declarations. And the other thing is you have to think about the binding priority. So the binding priority. And that happens if you have something like 1 plus 2 times 3. What do you execute first, plus or times? Now, for plus and times, this is predefined, but if you define such stuff yourself, then you have to define this priority. So let's do this. So now I define an infix function %%. You can see this is syntax for infix functions because these are sequences of special symbols. They don't start with colon. This should be a function from int to int to int. And this should simply be an alternative name for plus. So x, this operator applied to x and y should be x plus y. It's just a different name for it because we think that 2 times % is much more readable than writing plus. And similar to add, we think is a much nicer name for multiplication. So we could define something like this. We could say x, and then this operator applied to y gives you x times y. Now, of course, these are just different names for plus and times, but now we defined this stuff ourselves, and the question is, how should one evaluate the expression 1, and now this first operator, 2, and then the second operator, 3. Now, if you know that this is plus and this is times, this is 1 plus 2 times 3, but this is not predefined plus and times, but this we defined ourselves. And it makes a difference. If you first execute, I write plus above this and times above this, so we can keep in mind what this computes. If you compute this first, then you have 1 plus 2, which is 3, times 3 is 9. And if you compute this first, then you have 2 times 3, which is 6. And then you add 1, and that will give you 7. And so the outcome will be different depending on what you execute first. So what you should do is you should give a binding priority to your operators, and you should tell Haskell whether this has higher binding priority than that, or vice versa. If you want to do it in a non-standard way and say plus binds higher than times, you can do this, and then you would add the following declaration. You would do it as before with infix L or infix R, but in addition to the stuff that I wrote up there, you can also add a number here. You can write a number, and now the rest is the same. And this number is the binding priority. So this declaration says this operator associates to the left, and it has binding priority 9. And this other operator also associates to the left, but it only has binding priority 8. So this here is the binding priority. And the higher the priority, the higher the binding, and you execute those operators with the highest binding priority first. So the idea is operators with higher binding priority are executed first. And if the operators have the same binding priority, then you go from left to right. So if we would say both have binding priority 8, then you would first execute this because this is the leftmost operator. So if operators have the same binding priority, then the leftmost of these operators is executed first, is evaluated first. Then execution starts with the leftmost operator. And the default, if you don't add any binding priorities go from 0 to 9. So binding priorities, they are a number between 0 and 9. From 0 to 9. And if you don't add any binding priority, then it is 9. So 9 is the default. And I think the predefined plus and times have binding priority 7. So you have the possibility to define things that bind higher or that bind less high than plus and times.
I have a question. What's the priority of parentheses?
Of parentheses. Parentheses are above binding priorities. So if you want to execute the whole thing in a way that does not correspond to the binding priorities, you write parentheses, and they overrule any binding priority. Binding priorities only play a role if you don't have parentheses. Okay, so to have all this, we need to extend the grammar, yes?
Binding priorities are to establish a relation with other operators, right?
Correct.
So is there a way to know the binding priority of a specific operator? Or do we have to look up in the table?
You mean of predefined functions?
Yes.
Well, what you can do is you can look at...
That we are using from a library.
Right. Well, that depends on the documentation of the library. So if you take the standard library of Haskell, which comes with typical Haskell distributions, so if you just take the prelude, the prelude you have as a source code. You can always look into the source code to find it out, or you look into the documentation of your library. Different people write different libraries, and how well they document their library, that depends on the people who wrote them. So they should give you the binding priorities of the operators they provide. If they don't, then... well, you don't know the binding priority. Of course, you can try out, but that's not what you want to do. So you have to look into the documentation, and if there is no documentation, you can look into the source code. You just search for the infix declaration of this operator, but yeah, you need to know it if you want to use this in a sensible way. True. Okay, so to have infix declarations, there's a straightforward extension of this grammar. Now we can also have a declaration can also be an infix declaration, and the infix declaration looks like this. So this, these curly brackets in the grammar are just a notation to save space. This means you take any one of these. So instead of writing 3 rules, I just write 1 rule, and that means you either write infix or infix L or infix R. And then you have these, this means you can add this, but you don't have to. So if you like to, you can then write a number between 0 and 9, which gives you the binding priority. And then you say which operator should have this binding priority and should have this association. And you can write many operators here in order to save space. Instead of having a different infix declaration for each operator, if they all have the same binding priority and association, you can write just one declaration. And as I said, operators, so infix symbols, if they are variables, they are strings of special symbols that don't start with colon. If they're constructors, they are strings of special symbols that do start with colon. And one last remark before we end this section on declarations. Infix declarations you can also apply in a partial way. I mean, with prefix functions, we know how to apply them in how we do partial application. We simply don't provide all arguments. And that works for infix symbols as well. So partial application can be done here as well. So we can benefit from currying. For example, we can write something like this, +2. Now, plus normally takes 2 arguments, and you would write these 2 arguments. Well, first argument would be before the plus, second argument would be behind the plus. Now, if we write this is considered to be the function that waits for an argument and then would plug in this argument here. So if we apply this to 5, then the result will be 5 plus 2, which is 7. So this thing is the function that waits for an argument and adds 2. And you can also write something like 6 divide. Now, what is this? What value does this expression have? Divide is a function that computes division. If you write it with backwards, it's an infix function, so it would expect 2 arguments, and it would divide the first argument by the second argument. Here, the second argument is missing, so this is a function that waits for its second argument, and if you give the second argument to this function, it will divide 6 by this second argument. So if you give the argument 2 to this function, the outcome will be 3, because 6 divided by 2 is 3. You can also write something like this. Divide 6. Now this is a function that waits for an argument, and if it gets the argument, it will plug it here. So this is the function that waits for an argument and then divides it by 6. So if you give 12 to this function, the result will be 2. So this is not the same as this, because divide is not commutative. Here it doesn't matter whether you write +2 or 2 plus, this happens to compute the same because plus is commutative. Oh, this is nice notation if you have infix operators. Okay. Okay, so we've now seen how to build declarations in Haskell. And now this first chapter on introducing Haskell introduces the basic concepts, and the most basic concept are declarations. We finished this now, and the next basic concept are expressions. You remember that expressions are very fundamental. These are the things that we evaluate in the end, and this is also what we find on the right-hand side of function declarations. There we say a function applied to some argument equals some expression. So how do these expressions look like in general? So this is section 112. How do expressions look like? We had declarations, now we come to expressions. And expressions are indeed very fundamental. This is the most fundamental concept of functional programming. And if you type an expression into your Haskell interpreter and you press return, then what happens is this expression is going to be evaluated. So every expression can be evaluated, and every expression also has a type. So every expression has a type, and expressions can be evaluated to get some value. So in order to get it evaluated, you can simply type it into your Haskell interpreter and press return. So enter the expression into the interpreter and press return. Then this will be evaluated, and you will get the result, provided the evaluation terminates without any program error. And before evaluation takes place, first, the computer will check whether this expression is well typed, whether it's type correct. So if you just want to check whether it is type correct, in Hux, so Hux commands start with colon. So for example, :q means quit. Then you quit the interpreter, and :t means compute the type. So if you just type this and then return, then this will compute the type of the expression. Computes the type of the expression. And if you evaluate, first the computer will check whether the expression is type correct, and if it is, afterwards it will be evaluated. First, check whether expression is well typed or type correct, and then evaluate it. And only then evaluate it. So this is similar to other programming language with static typing. Before execution of a program, you do type checking. Java does this, for example, as well. Pascal would do this. And Haskell does this too. So if you want to evaluate your expression, it will first check whether this expression is well typed. Similarly for programs, if you load a program, then first your program will be type checked, and if it's not type correct, then Haskell will refuse to load this program. So how do expressions look like? Well, let's simply look at the grammar for expressions, and then we go through all the rules. So the simplest form of an expression is a variable. So what expressions do we have? We may have variables. So any variable which is written as a string with a lowercase symbol, or can also be an infix variable, is an expression. So for example, something like x, or something like square, or something like, what else do we have? Plus, and so on. All this would be expressions. And, well, for example, that means you can write expression, or 10 we'll get later. But all of this you can write as the right-hand side of a function declaration. Now, the next form of expressions are data constructors. So these are data constructors which are used to build the objects of a data type. Used to build the objects of some data type. And in Haskell, these things start with capital letters, so it would be something like true or false. These are the constructors of the data type bool, and they are predefined. If they are infix, they start with colon, and they would look like this, for example. And there's one exception to this rule. So this is a string of special symbols, but nevertheless, this is a data constructor. So this is an exception to the rule. This is also a data constructor, namely the data constructor for the empty list. And of course, you can define data constructors yourself. You don't know how yet, but I will come to this later. So there can be many more. And what would be the type of these of expressions which are constructors, well, that depends. So here the type would be bool. Here it would be bool as well. Here it would be a function that waits for some argument. Then it waits for another argument. And then it returns an argument. And the two arguments that this colon operator takes are some type, and the other argument would be a list with elements of the same type. So it might be something like 2 and then colon 3, 4. And so here A would stand for the type integer, and this would be an integer. This would be a list of integers. But you can also write something like true is going to be inserted into the list which already contains false. Now this would be a Boolean, and this is going to be inserted into the list containing a Boolean. So we have again this concept that you can have variables for types. We will look at this more closely later on. Now there are some more obvious expressions, namely the expressions of the basic predefined data types, integer, float, and character. So for integer, the expressions that I mean here, they look like this: 0, 1, minus 1, 2, minus 2, and so on. And these expressions have, as I said, every expression has a type. So this expression has type bool, this expression has type bool, this expression has this type, and so on. And now these expressions, they, for example, have type int. Type int. This is a predefined type. And similarly for floats. So floating point numbers, they are denoted like, minus 2.5 is an example. You can also write things in the usual way where you say it's 3 times 4 times 10 to the power of 23. So this stands for 3.4 times 10 to the power of 23 with an E notation. This is as in other languages as well. So I think this is the same notation as you would have it in Java, for example. So there's nothing special about this. This is standard representation of floating point numbers, and there's a predefined type for this called float. And you have characters as well. We didn't see them yet, but again, this works like in any other language. So characters would be written in apostrophes, because if you don't write this apostrophe, then this looks like a variable. A variable is a string starting with a lowercase symbol, and so to make sure that this is the character, these things are written in these apostrophes. So it would be something like this. You can also have capital letters. You can also have, well, any letter. And you can also have control. So something like this. When you write this backslash here, this means this is a control command for new line. So if you want to print things and you want to format your outcome, you have commands like new line or tabbing and so on. So this stands for new line. So this works like in other languages as well. And there's a predefined type for this called character. Char. So these are the most simple ones, and two more, and then we stop for today. And now these that I had up to now were very simple, but you can have, if you have expressions, you can compose them to more complicated expressions. And if you write something like this, expression 1, comma, comma, expression n, and you write this in square brackets, then this means this is the expression which stands for the list containing these values, the value of expression 1 until the value of expression n. So this means a list of n expressions. You can only write this if all these expressions have the same type. So they should have the same type. They should have the same type A, and then the result, this expression, exp1 to expn, then has type list of A. So an example is the list containing 1 and 2 and 3. Now this would have the type list of integers, or something like list of true and false. This would have the type list of booleans, but something like the list of 1 and true is not allowed, because these things don't have the same type. And the last thing for today, one special case of lists are strings. And strings are simply lists of characters. Lists of characters. So there's a data type string, and this data type is identical to a list of character. So this is just an abbreviation for this, and you can interchange this. This is exactly the same. So, for example, you would write strings like hello. So if you want to write the word hello in Haskell, it would look like this, because this is the list containing the strings, containing the characters H, E, L, L, and O. And since this is unpleasant to write, there's a shorthand notation for this. Instead, you can also write double apostrophes, and then you write hello. And that saves you some typing time. So for Haskell, this and this is identical. This is just a shorthand notation. And similarly, this and this is also identical. If instead of writing this, you can write string. Okay, so next week there's no lecture and there's no exercise on Wednesday. But on Friday, there will be the first exercise course. And we will see each other again the week after on Tuesday.